Okay, so today we're going to do the second part of my three-part series on basically the saltwater wedge, right? And so all of this, what's motivating this is that there is a saltwater wedge moving up the Mississippi River. So I already did a video where I talked about the pressure and what pressure is. In short, pressure is rho GH, and we'll talk a lot about what that means and why that pretty much defines what's going on with this saltwater wedge. Pretty much anytime you're dealing with fluids, pressure is the most important thing. It's usually almost always the driving force. Okay, excuse me, I'm drinking a little green tea. Okay, so, but this one in particular, we're going to talk about this estuarine circulation. And that is, of course, well, maybe it's not of course, but for me, it's of course, that is what is defining the saltwater wedge and where the wedge comes from. Okay, so let's start by talk. And then this last one will be I'm basically going to do this video again, but I'm going to do it with calculus. And when we do the third part, you will see both the power and the limitations of the calculus. Okay, so I'm not going to use this bit just yet, but we're going to get to that in a second. So right now, let's just talk about this estuarine circulation and what's going on, okay, in the saltwater wedge. Okay, so what is the saltwater wedge, and how does that have to do with the estuarine circulation? Okay, so what we see in a typical estuary, and I'm going to try to do this in black in general. Okay, so you might have some situation like this where, the river water, so here's the river water, this is the river over here, and it's got a certain density. So I'm going to write that as a rho. So this is freshwater density. And the river water is heading towards the sea. And in our case, that might be the Gulf of Mexico, but I'm going to make this more general. So I'm just going to call it the sea, right? And it's usually an ocean, but it doesn't have to be. So we're going to call that rho saltwater, right? So now the comparison of these two particular things, generally speaking, is that the rho of the freshwater versus the rho of the saltwater, okay, they're not equal. Okay, usually it's about 1.03. The saltwater is about 3% more dense than the freshwater. It's not really a lot, but it's enough, right? And so what typically happens, and this is where that saltwater wedge comes from, is that this denser water kind of wants to move upstream. It kind of flows under the fresh water, right? And so the fresh water typically kind of comes and it rides over the top. Okay, now it should be, this is like really, really interesting, and it's kind of like, well, why in the heck does that happen? Okay, and part of it has to do with this, right? It has to do with that density, okay? And so, as I said in the last video, the universal definition for this, why this happens, is people say, oh, well, it's, the salt water is more dense, so it wants to flow under the fresh water. And that of course, is true. But why? Like, why do we get this interesting pattern here? So here, this particular shape, as I'm drawing right now, this is the quote-unquote saltwater wedge. So this is the wedge. Okay, and it is just a wedge of saline fluid flowing upstream on the bottom of the river. But, I mean, so it's more dense. So why doesn't the river water, but the river water is still able to flow out over the top. So there's a physical reason why this happens that I think, which is what we're going to get into right now. So this particular pattern right here of, salt going upriver on the bottom and fresh going out on the top, okay, if I combine both of these, this would be called the estuarine circulation, okay? Circulation for obvious reasons, because the water is circulating in a kind of a pattern like that. And then estuarine, because this is an estuary, okay? So an estuary is just some area where the salt and the fresh mix. If you get into the literature on that, it's really complicated what they define as an estuary. But I think for the purpose of this video, it's just where salt and fresh mix. All right, so why does this happen? Okay, and so now I'm going to get back into the math a little bit. And we're going to use this definition of pressure. Pressure equals rho GH. Okay, so let's zoom in on that and let's stare at these things really, 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 really close. And what I think is really important here, there's two things in here that are very interesting. Okay, H, That's the depth within the fluid. Okay, so in other words, the deeper you are, the greater H is, okay, then the greater the pressure. Okay, on the other hand, this one right here, this rho, that's the density of the fluid. So the denser the fluid you are in, the greater the pressure, generally speaking. Okay, this G right here, that's just the acceleration due to gravity. So, that's just gravity. Okay, so 9.81 meters per second squared, or 32.2. Okay, so now what do these two things mean? So we're going to split these apart, and we're going to think about them both kind of separately. I'm going to think about something where rho varies and then something where H varies. And I'm going to start with H because I think it's a little bit simpler. Okay, so let's imagine that I've got a river, and I'm going to make this surface very steep, okay, just for illustration purposes. Okay, so here's our little imaginary river. I'm going to say that the density on both ends of this river is the same. So maybe this is somewhere, maybe this is just within a regular river, right? And so up here, right here, right, I'm going to use this equation right here. And the depth right here. So remember, depth is H is 0 because we're not anywhere below the surface, right? The same might be said right here. H equals 0. So H is 0 everywhere along this surface, right? Okay. Now, what does the pressure do as we drop through this fluid? So if I go down, some distance in this fluid, what is it doing? Well, hopefully you can see that based on this equation right here, the pressure increases linear with H. So the deeper you go, the deeper this goes, the greater this gets, okay? By what factor? What's the slope of that line? Rho times G, okay? So in other words, the pressure on this little dotted line that I have driven is a straight line, and it is just increasing. The slope of that line is rho times G. Okay, so normally we would draw this as kind of like little arrows going like this. Something like that. Okay? So that is we're essentially doing a free body diagram here. That is what is happening on the left-hand side of this block of fluid. Now, on the right-hand block of this fluid, right, there's fluid downstream of this block as well, and it is pushing back on it. Okay? Now, in the same way, for this particular block of fluid, I'm assuming the density is constant, right? We're just somewhere in a river. Like, it could be, we're in Baton Rouge or we're in, Minneapolis. It doesn't really matter. And we have the same thing, like this rho G is telling us what the pressure is like at a certain depth, right? So, the rho G is the slope of this particular, of that particular pressure line, okay? So this is all of our fluid in the inside here. And now what is the fluid going to do? Like, what is the pressure trying to encourage that fluid to do? Well, it should be obvious just by looking at it, that the pressure, that the total pressure force over here, the force from all this pressure, is greater than this particular force from all this pressure. Okay? And more to the point, at a given height, like if I were to, let's say, let me use a little blue here, but if I were to compare the pressure here to the pressure here, right, generally speaking, that pressure is going to push this way. You should be able to see that this arrow right here is greater than that arrow right there where it's 0. And everywhere along this thing, if I choose a particular height, and I choose a particular height, and I compare this arrow to that arrow, hopefully you can see that the pressure is always, we call this a pressure gradient, is always going to the right. And more to the point, this arrow compared to that arrow, if I've drawn this to scale, it's always going to be the same difference. So this arrow compared to that arrow, and this arrow compared to that arrow. So everything is going to the right, and it's always the same amount. So basically, if I took this entire thing over here, this entire pressure over here, and I added it to that pressure right there on a single line. So let's imagine we have a single line. That's not really a good idea, is it? Let's put where do I want to put a single line? Let's clear the inside here. Can I do that? I can kind of do that. Okay, let's add them up in the middle here. Okay, and maybe I can get rid of some of this. Okay, good. Okay, so I want to, in a single vertical line, capture what's going on if I compare this thing to that thing. So if I got a single vertical line in the middle, then basically this one is always greater than that one by some set amount. So if I were to subtract these two, I'm going to get a line, I'm going to get a vertical line that looks like this, where the left-hand pressure is always greater than the right-hand pressure by some set amount, okay? So this right here, this is a pressure gradient, okay, because this is a pressure gradient. It is the difference in pressure between, ooh, spelling is not coming to me today. So this is what we call a pressure gradient, okay? And basically, it is a constant. It is a constant through depth, okay? And so this pressure gradient is due to a difference in basically depths. Okay, so it is all caused by the fact that it is deeper over here than it is over here. Okay, and so this has a special name. This is called the barotropic pressure gradient. And where I'm breaking a rule of mind of, capitalizing random words. Okay, anyway, so that's the barotropic pressure gradient. So that is due to the fact that H changes, okay, the depth changes in the flow direction. Okay? Okay, so that is the barotropic pressure gradient. All right, so there's going to be, so that now we've dealt with what happens when the depth changes in the flow direction. So let's talk about what happens when the density changes in the flow direction, okay? So I'm going to isolate density. We're only going to think about density. Okay, so I'm going to draw, this is, I guess it's a weird river, right? Because it's got no slope to the surface. And it's got a bed going along the bottom. Okay, so now the depth is the same everywhere. However, now I'm going to kind of bring my colors back in because this is going to be a row there's going to be fresh water over here, and this will be salt water over here. Okay, so now in this case, for the fresh water, when I go up to the surface here, okay, H remains 0. Okay, same as over here in the fresh water. H remains, well, I guess we'll kind of stick with black. H is 0, right? So in both cases at the surface, there is no pressure. However, the rate at which the pressure changes as you go down is a function of rho g, right? So rho g is telling us how steep this line will be. So in this sense, we might have like this. Okay, let's just imagine. Okay, straightforward, I would imagine. Okay, now over here, however, the density is greater than the density is over here. So because the density is greater, the line is going to be steeper. Okay, now I'm going to try to exaggerate this just for demonstration purposes. Okay, let me put rho s over here. Okay, so we're going to exaggerate this. Okay. Okay, so now we've got, if I want to add up these two pressures on a single line, right? So if I wanted to put a single line right through the middle of all this, okay, and I want to add this pressure to this pressure, hopefully you can see that at the surface, they add up to 0. At the bed, this arrow, which I didn't draw compared to this arrow, is pretty large, right? So maybe it's like this. Okay, but in the middle, right, that one's compared to that one's pretty small, and then they progressively get closer to each other until they get to the top. So the net effect of this particular pressure difference is to cause things to want to go towards the fresh water from the salt water, but primarily towards the bottom, right, primarily towards the bottom. Okay, so this particular pressure gradient, okay, so this is a pressure gradient, but it is due to differences in density. Okay, and it has a special name. This is called a baroclinic. I guess I'll keep with my periclinic pressure gradient. Okay, and over here, the last one was due to was because of changes in depth changes in the flow direction. This one is because the density changes in the flow direction. Okay, so in other words, now we've got this weird system. I've got a barotropic pressure gradient, which is right here. And I've got a baroclinic pressure gradient right here. And both of these are happening in a river as it approaches the coast. So what I'm going to do is I'm going to take this pressure gradient and I'm going to add it to this pressure gradient. And that's going to kind of give me an idea of what's going on. Because in a real river, we have both density changes in the flow direction and depth changes in the flow direction. Okay, so let's combine this and this. Okay, so here we go. So here's our lovely river. It's sloping downwards. It's got a bed somewhere down here. Okay, and then basically I've got row fresh over here. I've got row salt over here. And I've got a barotropic pressure gradient, which looks like this. Okay, so I've got a bunch of little arrows. So this is my barotropic pressure gradient. So this is due to the fact that there is a slope to the surface. Okay, so because it is deeper on the left than it is on the right. Okay, and then I've got a baroclinic pressure gradient, which I'm going to draw over here. And wait, how did I draw that one last one? Okay, so, and it looks like this. Okay, and maybe if I want to make it competitive with the other one, I need to make it a little bit more aggressively sloped. So let's draw it like that. Okay, boom. Okay, assume I'm drawing a straight line, which I'm not, obviously. Okay, so if you add these two together, then what you end up getting somewhere, let's do this on this imaginary surface in the middle here, is near the surface. If we just start thinking about these things little by little, like look up near the surface. Okay, the flow is going to be outwards, right? It's going to be towards the saltwater. At the bed, okay, we're going to see it going upstream. So we will see this thing, and it will, obviously it depends on the strength of the relative strength of these two things, right? But we will see at the bed, we will see the density difference is more important. And at the surface, and up near the surface, we will see that the depth difference is more important, okay? And so right there, you can see that this is going to cause upriver flow near the bed and downriver flow near the surface. This is called, again, this is the estuarine circulation. Okay, or at least it's what causes the estuarine circulation. Okay. So this has some interesting implications. So let's draw just kind of a fresh river over here somewhere. So here we go. We've got a river and it's sloping and it's doing its thing. And if we've got fresh water over here and we've got salt water over here, and we've got this circulation going on, right? So the fresh water, because of this pressure gradient, because the combined effect of these two pressure gradients, the fresh water is doing this, and the salt water is doing this, right? Okay, and somewhere in here we might draw, well, I don't want to get too exaggerated here, but we might draw, an imaginary, okay, this is like the wedge, right? So there's a wedge. Everything above that is going out, and everything below that is coming upriver. Okay, so this may be, so there's a few things that I think are kind of surprising here, because we don't normally think of rivers as flowing upstream. But what it means, okay, and so I want to talk about a few different interesting things that happen because of this. And first, probably the most powerful one, the most important one is salt. But I just wanted to talk about, like, let's suppose, you're out in the Gulf of Mexico, and there's a giant, there's a oil thing over here, and it busts, right? And so the oil, all these hydrocarbons go out, and they find their way to the surface. Okay, and so you end up with this oil slick. Oil slick. Okay, and you're in charge of cleaning up the oil that has come out. Now, oil, as we know, is lighter than water. You know, you've seen that if you've cooked anything or whatever. And so the oil kind of sits on the surface, and the currents from the river take it out into the Gulf of Mexico if the spill is close enough. However, and I'm not a chemist, however, I know that there's probably thousands of different chemicals that are in this little hydrocarbon well. And so one of the things that comes out of this thing is what they call tar balls. And these are these little balls, and they're sticky. Okay, and I don't know what they look like or how big they are, but you can get, I've seen pictures. Anyway, and what you can imagine, perhaps based on what I've just told you, is that these little tar balls are going to generally, thanks to the currents that they're in, they're generally going to work their way upriver, which is, surprising. So if you are looking for the tar balls, if you're trying to clean up all the hydrocarbons that have, created a mess on your coast, you need to look for the tar balls moving upriver inside of a river. Okay, they're denser than water, and they're big enough that they're not going to, somehow bounce up here and get carried out. Okay, so that's one interesting thing. Okay, another interesting thing that comes about because of this is, let's imagine you've got a little piece of sediment. Okay, your sand or silt. Now, sand, for example, row sand, is equal to about, 2.65 times the row of fresh water. Okay, so the row of a sand, generally speaking, is these things like to kind of sink. Okay, well, what happens if you are a piece of sand and you're moving downriver, and all of a sudden you run into this? Well, generally speaking, you might start to, kind of pile up right here, right? Because the currents upriver are pushing you downriver, and the currents downriver are pushing you upriver. Okay, and so you might kind of pile up right here. Okay, and the same actually, well, to a lesser extent, will happen with the mud, but the mud, i.e. the clay and the really small particles, are much less dense. And anyway, so you might pile up in a certain spot. This particular spot would be called an estuarine turbidity. I'm capitalizing this one on purpose, turbidity maximum. So this is typically abbreviated ETM, and that's why I put it here. So there's a spot in the river, and there might be multiple spots depending on the, on the density gradients and things like that. But there is a spot where there's a lot more sediment that just kind of holds up there, right? And it might sit there for a while. Now, we must remember that the whole bed is generally made of mud and sand dunes, depending on the river. But anyway, what will happen is the sediment will basically accumulate there. And then in the spring, you might get, when the spring flow comes through, spring flow, okay, then all of a sudden, everything changes. And instead, when you get the spring flows, basically the river gets steeper. I'm exaggerating here. And everything flows out. Okay, and the location essentially of this estuarine turbidity maximum is going to be moved way out towards the Gulf. In fact, it might be big enough that this entire wedge just gets pushed out towards the Gulf. If the free surface gets steep enough. Okay, the last thing that I think is really interesting here, and I guess for salt I'll use red, is that, well, okay, cool, but this salty water that's coming upriver, isn't it going to also create basically like a salt maximum, right? Wouldn't all the salt just kind of, if it's continually flowing into this spot, isn't this spot just going to become like extremely excessively salty, right? And I think that's a really interesting thought. But salt is not sediment. I mean, it's not sand, right? It does not. I have no idea what the density of the salt is. But it's because it's not really important because the salt dissolves. And so what you will see is that the salt will, I'm drawing it as if it's coming out of the sediment, but let's imagine we had the salt will, because of turbulence, it will mix out. So it will slowly mix, not slowly, it can be very quickly, but a lot of the salt will mix out and it will dissolve into this fresh water. And as soon as it dissolves into the fresh water, right, it will join the fresh water on its exit out. Okay, as long as it doesn't make the water above it so salty that it breaks up the whole pattern. Okay, so what would cause this turbulence? Like, why would the river be turbulent? Like, why do we have these things? Okay, and I should post a video of what these eddies look like. Although you can probably just go to YouTube. Go to YouTube and just type in eddies, and you will recognize them from your everyday life. From if you stir coffee, or if you I don't know. I mean, there's so many million places where you might see these eddies. You can imagine what these things look like. But basically, there's this energy, basically right along this interface, right along the salt wedge. Okay, that's one place where there's a lot of energy. There's also a lot of energy because there's a lot of friction along the bed. Okay, and you also get a lot of energy along the surface. Well, do you? Well, not usually. But anyway. And what happens is, in these locations, you get this turbulent energy, and you get these eddies. And usually they're kind of drawn like this, like a bunch of, interlocking swirls. In fact, I think this is how, I think Michelangelo, or one of the great Renaissance guys, drew them like that. And so what you can imagine is, if there's any kind of swirling going on, is that this fresh water is being carried down into the salty water, and the salt water is being carried up into the fresh water, right? And so that makes this, it just mixes it out. Okay? And so one of the things that this does, this turbulence, is, so in the Mississippi River, generally speaking, I'm going to draw what's called an isohaline. Okay, so I'm going to draw some isohalines. Okay, so here we go. So in the Mississippi River, if we've got a saltwater wedge, you might have a line that looks like this, and this is an isohaline. Oh, isohaline, excuse my bad drawing. Isohaline, or haline, I don't know how you say it. And you might say the salinity everywhere along that thing is 35. Okay, so 35 is about freshwater. I mean, it's about ocean water. Okay, and then somewhere upriver, you have another one that looks like this, and you might have the salinity there is about 30, right, or something, right? So this might be the shape of the isohalines for a salt wedge estuary, where you can see the shape of the wedge and the shape of the isohalines. Okay, now, on the other hand, if you were in a more energetic system, let's suppose you were in Puget Sound in Washington State, okay, the isohalines there might be like just straight vertical lines. Okay, so this might have a salinity of 35, this might have a salinity of 30, this might have a salinity of 25. Now, why is that happening? Well, the reason for that happening is that, all those same pressure gradients, the estuarine pressure gradient and the slope of the system, and, so the baroclinic and the barotropic, all of that is happening, right? So the salt water wants to flow underneath, and the fresh water wants to flow over the top. Oh, I wanted to do that in blue. The fresh water wants to flow over the top. However, as soon as this salt water, gets a little toe, and as soon as this fresh water gets a little toe, the problem is the system is so energetic, there's so much turbulence, that this water just kind of mixes, and this one mixes down, and all of a sudden everything is vertically mixed again. Okay? And so this right here is called a well-mixed estuary, and it's because there's so much energy that it cannot become a wedge, right? This is a salt wedge estuary. Okay, and then they have a lot of other different variations on these, and I think what's important for you guys is to recognize that these things change. Okay, in time and space. Well, really mostly in time, right? And location in the estuary. So, for example, sometimes, estuaries will look like this, when the tide is moving really, really fast, because you have a lot of energy, and then all of a sudden that energy gets converted into a way to make the isohalines vertical, right? And then there might be a time when the tides die, or maybe there's low river flow or something like that, and it becomes a salt wedge because there isn't enough energy to keep things well mixed. Okay, so the last thing that I'll leave you on is one of the things that the Corps of Engineers is doing is to maintain your water drinking supplies. So if we imagine that this is the river, and we imagine this is the fresh water, and it kind of comes up over that wedge, right? And here's the wedge, right? So the fluid is trying to flow upriver on the bed. So one of the things that they will do is they will put in what do we call a sill? So a saltwater sill underneath the river. Okay, with the idea here being, hopefully, well, a few things are going to happen, but we're concentrating this freshwater flow over the top, and hopefully then the salt water will just kind of pile up here, right? So this will all be salty water underneath, and sure, every now and then some of it will mix vertically, and it will be ejected with that freshwater flow over the top. Okay, that's one of the things that they've done. I don't remember exactly where this particular sill is. But anyway, I hope this was interesting to you. I didn't learn about any of this stuff till grad school, so it's kind of a lot. But this is the picture that I want you to have. This is what's going on. And what I think is really powerful is the fact that the flow is over the top because the water is deeper upriver, and it's upriver on the bed because it's denser downriver. Well, that's all I got. Hopefully this was interesting to you, and this was my take on the old estuarine circulation, right? And I guess we should be red and blue. Okay, so if that's interesting, cool. Hope you liked it. All right.